Cool. Hi, everyone. So this is the first in our amazing kind of series of lectures as part of concurrent in two things. One in our UW Reality Lab, which is a VR AR lab here, and the other part is also for students at the VR AR capstone, which we have just started last week. So welcome, everyone. So my name is Ira, the ones that I don't know here. I'm super excited to introduce Tom Furness to give our first lecture. I can't imagine anyone who would be a better fit for a first lecture in a distinguished VR AR lectures. Tom is a professor here at the UW, pioneer, working in VR, working in the field since developing the field since the 60s, which is pretty insane. It started from working on HMDs for pilots, I guess, right? And showing 3D information inside the head-mounted displays for pilots in the 60s. And also inventor, entrepreneur, and so on. So really amazing task kind of things. And so we're really happy to have you here.
Thank you, Ira. Thanks everyone for coming. Isn't this a beautiful building? It's an amazing place. It's sort of great to have it here on the campus, and especially it's the home of the Reality Lab. This is sort of almost a reincarnation of some things that were happening a long time ago in the original HITLab at Fluke Hall. We were the first residents of that building, and but now this is just fantastic. And I think we have quite a mixture of folks here, certainly from the capstone, and also some of my students are here. I hope they're here. How many of you here from my class? Okay, because they're missing my class right now, so I can do this, that's why. I'll catch up with them later, the others later. Okay, so, lifting humanity. Now, I think a lot of us in this, especially the people that are in engineering and computer science and things like that, really want to try to do good in the world, don't we? We really would like for the work we do to contribute somehow to helping mankind. And so all of us really are in our own way trying to save the world. But I sort of wanted to give you my trajectory through this space and sort of the things I've learned. Each of you will have your own stories. And those are sort of beginning, you'll make your story. And hopefully your stories will lift all of us. So I want to introduce three guys. These are my contemporaries when I first started off in this space. There was an old fellow by the name of Mort Heilig. How many of you have ever heard of Mort Heilig? Okay, Mort Heilig, thank you. Mort Heilig was a filmmaker. And he basically decided there's not enough sensory input coming from film. And he wanted to actually add some more senses. Not only the visual, but he wanted to do visual in 3D, and he wanted to do sound. He wanted to do sound in 3D. He also wanted to do smell. He didn't work on taste too much, but he wanted to have a tactile, wind blowing on your face, things like that. So he worked on what is called a sensorama. Here you're actually sitting in front of it, sort of like a kiosk, where you put your head in this, you sit on the chair would vibrate, wind would blow in your face, you'd get smells, you'd get 3D, and basically playing a film. So he had built this camera that would record a lot of these things. Pretty cool, actually. So he was with us for a while and sort of inspired this whole idea that we are really multisensory beings. And that's the way we basically perceive the world. Well, then there's this guy by the name of Ivan Sutherland. I'm sure more of you have heard of Ivan Sutherland. Ivan Sutherland, computer science person, started out at MIT, went to the University of Utah, formed a company with David Evans called Evans and Sutherland. And they were big into computer graphics hardware. He did some early work trying to figure out a better way to interface humans to computers because everything was in 2D. How in the world could we make this 3D? And not only how could we make it 3D, but how could you go inside these 3D objects? So he did some early work in that. And he preceded me, what, about 5 years or something like that, in terms of birth. And here you have Lieutenant Tom Furness. Lieutenant Tom Furness, I grew up in Western North Carolina, you could probably tell by my accent. I went to Duke University, got a degree in electrical engineering. This was during the Vietnam War. I had a 1A draft status, which meant I was going to go in the military regardless. I didn't have any choice. But I could get a student deferment, which meant if I went to school, I wouldn't have to go for a while. But as soon as I finished, I got commissioned in the Air Force as an officer, second lieutenant in the Air Force. So here I am standing at the Wright-Patterson Air Force Base where I had my first assignment. And basically my assignment had to do with fighter airplanes and how do we interface pilots to fighter airplanes. So what I'm going to do today, in the time that I have, is try to rush through a few things, but I want to get questions from you because you might have some questions as you go along. Just sort of hold them until the end and then you can then lay them on me. But I had these 4 phases of my attempts to save the world. And let me just speak to a little bit to each of them. The first was basically making a sword to begin with. Well, here I was, a brand new second lieutenant in the military, and my job was to figure out how to connect this person to this machine. Very complex machine. And when you're in this machine, you're doing things like looking at this. There are 75 displays, 300 switches, 11 switches on the control stick, 9 switches on the throttle. You're flying twice the speed of sound, pulling G's to the boundaries of consciousness, and being shot at the same time. Sort of a busy day at the office. So not only were you sitting in this and trying to understand how this works, this is what you're doing. So you have all these dynamics you're dealing with, flying upside down. You look at this guy, he's looking out of the cockpit. You want to spend as much time looking out of the cockpit as you can because you don't want to have an encounter with the Earth at a high speed, or another airplane for that matter. So this is a very difficult job. And how do you build a workstation that actually solves these fundamental problems? And these were a few of the challenges I was trying to deal with. We were having to aim the whole airplane in order to steer the systems on the airplane, to aim things. We also had a problem of seeing at night. When you're flying at night, low altitude, high speed, how do you see then? How do you deal with all this complexity? And also, how do we do this relating what's in the cockpit to what's in the outside world? So we came up with some solutions for these. The first was, how do we address the aiming problem? Here you have a situation where, this is one of the aircraft I was flying in. It's a Phantom. The problem was you have to aim the whole airplane or aim the systems on the airplane. All these sensors that you have here, and of course the weapons and things like that. Well, I started to work on this to come up with a way to solve that problem. And here you see Lieutenant Furness wearing the world's first helmet sight system. What this is a gadget that fits on top of your helmet, and it has 2 lead sulfide photodiodes on the side of the helmet here. And what happens is you have a little pipper here that projects an infinitely collimated reticle at optical infinity. And when you move your head over that object, you place that circle over a target, then what we do is triangulate on each side of the helmet to tell you where that vector is that lines up with your pipper. And we can do that in real time and track with all kinds of degrees of freedom. So this is the very first Air Force head tracking system to help us solve that problem. What we did is we went and tested it. And we found out there's an F-106 aircraft when we're pulling Gs up to 7, 8 Gs and having target angular rates running through about 20, 30 degrees a second. We're measuring how this pilot was tracking those targets. Here's the helmet with the sensors on the side. Here's a scanner on the canopy rail, infrared scanner. And we found out these pilots were tracking with basically 0 mean error. It was amazing. This is better than the sensors could do. Humans, once you give them the proper interface, can do amazing things. So we found out it really worked and really worked well. To aim various systems in the cockpit, input information to the computers, things like that. So now you could look way off bore sight without having to aim the airplane, which was a big deal. Okay, so that's sort of the tracking problem. Then we have the seeing at night problem. How in the world are we going to do that? Well, of course, the problem with these cockpits is you don't have a whole lot of space. This is just sort of a notional diagram that shows the canopy rail here, all these instruments that you saw before. And because all the instruments there, there's not enough space to put a display. It's not big enough so you can actually see it. Because that real estate in a fighter cockpit is the most expensive real estate on the earth in terms of per square inch. What it costs if you want to move something, excavate it, and put something else in its place. So the problem was the pilots could actually see at night through forward-looking infrared, low-light level television sensors, but the picture wasn't big enough for them to see it. So how do we solve that? Well, turns out that we have this whole notion of virtual images. Now, virtual images are there all the time. When you stand in front of the mirror every morning, you see a virtual image of yourself. That's not really you there, but it appears to be you. So here we have reality and virtuality. This appears to be mountains upside down, but they aren't really there. They just appear to be there. So how can we take that into account and use it? So here's Lieutenant Furness wearing the first helmet-mounted display. In this case, we had a miniature television picture tube on the side of the helmet that generate a raster pattern, and then we relay that raster pattern with optics up to the eye. This is one eye display. So it was magnified, collimated, and projected, so it appears at optical infinity and subtends a visual angle of 30 degrees, when before you had about 5 degrees. And now you have 30 degrees, and you aren't taking up any cockpit space with this virtual image. Now, what you are doing is you're putting 15 kilovolts on the side of the helmet, and you have to have a quick release mechanism, because you don't want to punch out of that aircraft with this thing dangling on the side of your head, right? You know what I mean when I say punch out of the aircraft? That means if you have to leave the office really fast. And so that's one of the problems. Also, you have a problem with wind blast. What happens when you eject when you're going fast? Guess what? The wind sort of blows against you, right? And if you're flying, near the Mach and you eject, your head blows off. You lose your head. Because you're generating over the top of the helmet lift several hundred, 600, 700, 800 pounds lifting on your head because of the airfoil effect. We had to take all these things into account. Also, if you're on the apron and you have to get out of there in a hurry, you have to pull the cable and unleash it. Well, if you're in a fuel-rich environment, you don't want to create any sparks, right? So how do you build a connector that you disconnect 15 kilovolts, electromagnetic deflection, without creating a spark? So these were just some practical problems we were trying to deal with. So doing that in an aircraft is a lot different than doing it on the ground in terms of the problems you had to solve. Okay, well here we're now, instead of having that little 5-degree display, we had a 30-degree display. And oh, by the way, you can move it anywhere you want to move your head, because now you're not restricted to looking at one particular place in the cockpit. So we started thinking, well, let's put these two together. Let's put the tracking system, the infrared tracking system, along with the display. Now this is a different display. Here we have the miniature cathode ray tube here in the back, and it relays the image with a coherent fiber optic bundle over the top of the helmet into this paraboloid, which is the visor. It projects first into this spot, in the paraboloid, into a mirror. It's at the focal point of the paraboloid, back into the visor and into the pilot's eye. You can build two of these, so it's binocular. So it's a double bounce off the visor. The first bounce is an aspheric corrector for the second bounce. It's beautifully elegant. So when you switch this thing off, you can't even tell you have a head-mounted display on, or a visually coupled system. So here we now not only could move your head around and get that display, but we knew exactly where it was. because we're tracking where that head position was. So therefore, what we could do is use that to aim the sensors wherever we move our head, and then we get the image in that direction. So it's like we had a picture window to look through the cockpit at night with infrared eyes or low light level television eyes. This was transformational. And again, I was flying in these aircraft testing these things. But then we added one more thing. You know, it's not natural necessarily to aim things by aiming your head. What you want to do is be able to look at them, and that should be good enough. So we started working on this same parabolic visor combiner and putting a camera and an infrared source that projects light into the eye, infrared light, and then we'll look at the reflections from the eye and track it. So now we know the position instantaneously of the eyes in the helmet and the helmet relative to the aircraft. So therefore you had the absolute line of sight in space where you're looking, just with your eyes. And you use that to control switches. You can use that to select different functions in the aircraft and so forth. So let's fast forward a little bit and look at this whole issue of the complexity. You know, what do you do with 75 displays and 300 switches, 11 switches on the control stick and 9 switches in the throttle? Oh, by the way, those switches change what they do depending upon what master mode you're in the aircraft. If you go into a different mode, the switches do something different. And so it is very difficult to solve that problem. So this is where a few years later, I started working on the notion of the super cockpit, which is a cockpit that you wear. Magic helmet, magic flight suit, magic gloves that basically presents three-dimensional information to you and you interact with it naturally. So here we have an F-16 aircraft, 50 computers on board, one pilot interacting with 50 computers in real time. So you have a computer for your air data, you have a computer for your digital fly-by-wire, for your propulsion management, for stability augmentation, for your threat systems, so forth and so forth. There are 50 of them. If you had a power failure in the main power bus of that aircraft, it just isn't going to be a good day, because the airplane tends to swap ends. It's on the fringe, right on the fringe of stability. And you do that so that it has its performance. But you have to have the computers to stabilize everything. So what happens if you lose power to that, the airplane tends to swap ends. The blunty end goes to the front and the pointy end goes to the back. And you're going to have to leave the office really fast. So how do you deal with that? This is an F-18 cockpit. Now we're going to all kinds of electronic displays. And oh, by the way, you say, well, doesn't that simplify things? No. Because now you could put many more symbols up here. You push one of these buttons, you get a whole different set of symbols. And you have to know what they do. The manual for the F-16 radar is that thick. 60 modes you can call up on the F-16 radar alone. And, you know, when you actually get down to it, the pilots will use 4 or 5, but they're all there, and you have to know what they do. Sort of like Microsoft Word, you know, and all the options that you have there, what do you usually use, you know? So that's the problem we're trying to solve. Now, the way I went about it, that was my responsibility in developing advanced cockpits. So what did I do? Well, up to this point in time, the pilot was the last thing that people thought of. You build an airplane, you build a cockpit, and then, oh, by the way, you put a pilot in there, you have to learn how to use all that, or she. So what we did is went back to the basics and started from the human and worked out. So we took a typical Air Force pilot, and we took a typical person. And we basically, I spent $1 million of the taxpayers' money. I hired the world's authorities in human perception and performance. And they built these books, made these books of interactive perceptual information, integrated perceptual information for designers. They still exist. You can order them out of DTEC. And so from that, we learned a lot of things about people. And it really boils down, the $1 million boils down to about a few things. Number one, humans are three-dimensional beings. We see, hear, touch in 3 dimensions. Anytime we deviate from that, we have to learn something. Another thing we have to understand is we're all different. We have different shapes and sizes. We have different likes, dislikes, different cultural backgrounds, things like that. We have 4 eyes. We actually have 2 visual systems and 2 eyes. That gives us 4 eyes in the way that our eyes work, and I'll explain that a little bit later. All of these kind of things we began to understand. So then we decided, okay, how would we build an ideal cockpit to get bandwidth to and from the brains of these crew members? Because the reason you have the crew member there at all is because the human is the adaptive element in the system. They're the ones that make the decisions, because things don't always work the way you think they're going to. Otherwise, you just program a computer to do this. So the human is the adaptive element. So we built this super cockpit. The idea of the super cockpit, again, is you put on this magic helmet. We had lasers that actually project into a holographic lens, and stereo. We had binaural sound in here, speech input, hand tracking, finger tracking, tactile displays, tactors that were in the gloves. So what you'd have is basically you put on this flight suit, plug in, you have a 3-dimensional world represented to you. And you interact with it by looking at things, pointing at things, saying things in order to operate this complex system. So the whole idea was to turn this into this. This is what the pilot would see at night, flying at low altitude, high speed. It's greatly simplified, isn't it? But all the information that you saw in that other display is in this one. Only it's organized and portrayed in what we call a mimetic display, in that it mimes the world, it acts like the world. So you could tell, for example, as you fly along, this is a stored terrain database, data map. You see as you're flying along, you see these barber poles here. As this moves along underneath you, you know exactly what your altitude is and your speed without looking at any instrument. It becomes intuitive. You see the pathway in the sky automatically computed to avoid threats. This is a threat that's radiating. Do not fly through the red dome. The probability of survival is really low if you fly through the red. Okay, here's the hillside, all this terrain. These are 2 surface air missile batteries that are not radiating, but they're there, you know, from your intelligence. Here are 2 friendly aircraft, you know they're up there. Here's a possible enemy aircraft. You don't know who that guy is. You squawk a code form IFF. IFF is identification for info. You know, you say, who are you, electronically? And if they don't answer back, it's not good. Or if they give you the wrong password, okay? So here that's highlighted. Here's the compass rose where it really is in the sky, and then the weapons stores, all the other information you have in this 3-dimensional panoramic virtual world at night. Daylight, you see through it. We never had the difference between AR and VR in the old days. It was all just one thing. We just changed the transmission of the visor, and it was all the same. So, in addition to that, we also had this so-called God's Eye display. So you have an inside out and outside in display. So in your inside out, you basically see the virtual world through your headgear and things like that as you're looking around. But we also need a God's Eye display. And this is sort of like a hemisphere that sits on your lap. And you see the whole world sitting right there in your lap. And the way you would interact with it is you would reach out and touch things. And you control your communications that way. So you point at an object you want to communicate with, and you automatically encrypt it, the communication, and that takes place. Also, we had R2-D2 in this cockpit, by the way. We had an expert system that would be a pilot intent inference engine that would tell us when what the pilots, they try to infer what the pilot's trying to do and organize the world for them in real time to help them do that. We also had a problem with a G loss of consciousness, what we call G-lock. Because you pull enough G's, you'll black out. And so we wanted to know all the time if the pilot's conscious. And our head lolling indicator was if the head began to loll down like this, we're saying, ooh, that's not good. And so what we do is create a slap, a sound in the headset. If there wasn't a startle response on the part of the pilot, that meant they were out cold. And then the computer would take over and fly the airplane. We've lost so many aircraft in because loss of consciousness. So these were all built into this super cockpit. In this case, if you are now seeing an object that you're interested in your God's eye display, where is this in the real world? You point at it and this laser line would come out of your finger and you see where it is in the outside world. We've never been able to do that before.
An actual thing on
It's virtual. It's projected from your display and you see it there and you actually reach out and touch these things. Yeah. Well, that's all good theory, but does it really work? So we had to build a simulator to test these ideas before we put them in the real airplane. And this is my Darth Vader simulator that I built in 1981. What it did was we used this pancake optical system, which is pretty amazing in terms of collimation. And we took these 2 miniature cathode ray tubes, water-cooled electronics. We had to cool electronics because we're moving that raster line really fast. And we project it so you see a total of 120 degrees instantaneously by 80 degrees and stereographic. And this was in 1981 when we turned this on for the first time. This is all connected to a 16-bit electromagnetic tracking system and to 8 VAX computers and 2 PDP-11s attached to 2 Evans-Sullivan picture systems. 1 to draw the left eye, 1 to draw the right eye. This is all vector graphic at the time, and so that you get these virtual worlds. And this is what we used to test the concepts in the laboratory before we went out and test them in the real aircraft. Let me play you just a short video that was taken by Nova when they came to my lab one day. See that.
And inside what must be the zaniest helmet ever devised, this is what the pilot sees. Like some fantastic arcade game of the future, the pilot flies through a world that the computer has devised for him, based upon the known characteristics of the F-15 and its potential adversaries. In this Tron-like 3D arena, he can take off and land, navigate to preset coordinates, and he can fire his guns if need be, there is still a gun, and activate his missiles, all by voice control. Selected. The engineers readily admit that these futuristic concepts are likely to remain impractical for at least the next 8 to 10 years. And clearly, no pilot could be persuaded to dogfight pulling G's with a ridiculous contraption like this on his head. But it is only experimental, and advances in miniaturizing the high-resolution TV screens that will project the graphic displays onto the inside of the visor have already led to the development of a new and much more feasible flying helmet currently under test. But even more unusual ideas are being developed at Wright-Patterson. This man is switching switches simply by looking at them. Using infrared lasers, sensors in his helmet read his eye position from moment to moment so that computers can identify the switch he's looking at. And down the corridor, the tiny magnetic fields given off by the brain activity of this research volunteer are being analyzed by a superconducting device known simply as SQUID. Controlling fighter aircraft systems simply by thinking is, some researchers claim, no more than 30 years away.
Okay, when do you think that movie was made? Pretty close. It was made in 1986, I think, 1986. So if you do your maths right, what does that mean? Well, it turns out my last trip to my old lab at Wright-Patterson Air Force Base, I went into their new simulator, and it was amazing. All this huge dome projection system. this cockpit on a hydraulic lift. They put this band around my head and asked me some questions to think this, think that, think that. And then they said, okay, now you can fly the airplane with your arms folded, just by thinking about it. Now, it's not going to be in the inventory for a while, probably, to do that, especially if I have errant thoughts or something like that, you know, might not be good. But it can be done. And direct brain interfaces, as you know, are happening. Okay, so all of this, that helmet was not practical, but this is the helmet, one of the helmets that we built. And we wanted this to be, you know, take into account all of the technology we could at the time to make it lightweight, really strong, and we wanted to look cool. And so what we did was we hired Lucasfilms, the industrial designers, right after Star Wars, to design a sexy helmet for us.
Great idea.
And so this is one of the designs. One of them had lightning bolts painted on, sky blue lightning bolts, you know. It was really cool. And of course you have to understand that pilots need to look good. They have to look, you know, they have to have the silk scarf, cool helmet, things like that. So this one now, again, is a compound paraboloid here, projection into the visor, has the tracking system in it and everything, and it weighs 2 pounds, which is the time for an Air Force helmet. Furthermore, aerodynamically, it's beautiful. This little rim here acts like a perfect air dam spoiler for the helmet. So now instead of 600 to 800 pounds when you eject, you have a mere 200 on your head. So these were the things that were going on in my life when I was trying to save humanity. Now if you go look at the F-35 aircraft, the Joint Strike Fighter, guess what? It's there. This stuff is there. Took a while to get there, but nevertheless, that early work that I was doing is now actually in the inventory. Now, something happened. In 1988, 87, 88 time period, I got a call from a general officer from the Pentagon. He said, Tom, I've been watching your work, and we decided we need some positive publicity. The Defense Appropriations Bill is coming up, and we're going to get hammered because it's just come out of the news that the Navy is spending $800 on toilet seats. The Army is spending $500 for hammers. I don't know if you old guys may remember that when that was going on. And they said, we're going to get hammered with the appropriations bill. What we usually do is we release something black that we've been doing, a black ship, black airplane, to show the taxpayers that we're spending their money really well to protect the country. But we don't have one of those this year, but we have you. We would like for you to write a press release and hold a press conference of what you're doing in this virtual stuff, this virtual cockpit stuff. And I said, well, you know, it's all classified. And they said, declassify it. It's all show business, you know. So I said, okay, and I wrote up something, and sure enough, the CBS Evening News comes in, Dan Rather, crowd, David Martin, the Pentagon correspondent, with a film crew, and they spend 2 days taping what's going on in my lab. So I ended up on CBS Evening News, explaining this super cockpit stuff. Well, that opened Pandora's box, because after that, then NBC had to come, and ABC, and CNN, and CBC, and BBC, Australian television. Science editor of the New York Times came down and spent a day with me. We're on the front cover of US News and World Report. I was writing articles for Popular Mechanics magazine. And anybody that flew by over Ohio ended up in my lab, I'm convinced. We also had the general switch. When the generals came to visit, I had a special switch. I throw the general switch and they never missed their targets whenever they were operating their systems, you know. They were so good, you know. So, but as a result of all this, I started getting phone calls. I got a phone call from my mother. She says, I watched this program on television. You were talking about what you're doing, and my child has cerebral palsy. Is there anything you can do with this technology to help my child? And then a surgeon called me. Says, I'm a thoracic surgeon. I'm trying to do a graft of the aorta. And I'm into this patient up to my elbows, trying to find my way around. And my navigation system, which is my CT scan, is on a light box on the wall. Any way you can sort of put that in my display so I can see into the patient? Then another surgeon said, well, I'm trying to perfect an minimally invasive surgical procedure. I want to be in the inside looking out. Is the way that you can put my eyes inside the patient. Then a firefighting company called me and said, we have this problem with firefighters. They're going into these buildings filled with smoke. They don't know if there are any people in the building. They can't see through the smoke. They can't see each other. They don't even know where they are in the building. And the fire chief is trying to vector all of this, manage all of us, has a radio, and outside the building, he doesn't know anything. Any way you can solve that problem. Remember a few years ago, we lost 12 firefighters here in Seattle because they were standing on top of the fire and didn't know it. It caved in. We lost them. So I was getting 3 or 4 phone calls a week from people like this. And my answer to all of them was, well, yeah, you could do that. Matter of fact, that'd be easy to do compared to what I'm trying to do. And I realized at that point, you know, we're onto something really big. This whole virtual interface thing that can be transformative, because we knew it was an amazing way to accelerate learning, to get bandwidth to the brain, and you never forgot it once you were in one of these immersive virtual worlds. So that's when I decided we got to get it out of the military, because we could probably do a lot more good with it outside than inside. And I put together a plan to set up a laboratory somewhere in the United States at a university where all this money the taxpayers have spent on me could get out, and we can do something good with the technology rather than just building weapons. And so I sent my plan to MIT and Caltech and Stanford and Carnegie Mellon, University of Texas, University of Utah, University of North Carolina, here. And the dean of the College of Engineering phoned me and said, come on out and talk to us. So I did. I walked into his office, and there was another guy sitting beside him who looked familiar. And he was actually the executive director of the Washington Technology Center. He introduced himself to me. And I said, don't I know you from somewhere before? He said, yeah. I used to be the chief scientist of the Air Force. And I've been to your lab at Wright-Patterson Air Force Base. We want you to come here and do that here. So in 1989, I decided to beat my sword into a plowshare and come to the University of Washington and start the HITLab. Started Fluke Hall. You know where the makerspace is in Fluke Hall? That used to be where my lab was, part of it. It was also on other floors. Well, in the process of doing that, some wonderful things happened. Just in summary, and I'll get to some specific things, but in summary, the whole idea of the lab was not only to develop technology, but also to get it out there. That my report card was based upon how many companies we'd spun off, how many patents that we generated, and how many people were employed in the state of Washington as a result of that. Now, after this period of time, we have spun off 27 companies. 2 of the companies are traded on NASDAQ at a market cap of $12 billion. Over 300 patents, and hundreds of students. And that's you guys. The $12 billion worth. But there have been some interesting things along the way. It worked. The plan worked. When I first started, nobody really knew what virtual reality was. So it was clear that we had to do something about that. So what I did was put together some of my ideas to build a consumer virtual reality display. And this was my patent in 1992, what is called a display system for head-mounted viewing transparency. And what it does is takes a vacuum electrofluorescent rear illuminator, liquid crystal screen projected down to a prism, and what you now see is a virtual image of that original LCD screen at 1 meter wide, 3 meters away. And of course it moves around when you move your head, and this is all connected to a pack here. So we started a company called Virtual Vision. Virtual Vision was built and marketed this display. I was on the board of directors of the company and the inventor. And here's a person wearing the display. Here you see the headset and this belt pack that had batteries in it and a television receiver. At that time, television actually broadcasts to the air. Did you know that? It's pretty amazing. You can actually put it on the air. Here it is. Looks like a HoloLens, doesn't it? And this is in 1993. You put this on, you plug it into your receiver here with your little antenna, right? And you can watch Oprah while you're sitting on Waikiki Beach. Why you'd ever want to do that, I don't know, but you could do it with this. So we raised a bunch of money. We're at the Consumer Electronics Show. People lined up for 2 hours to see this thing. Everybody's saying, gosh, you're going to make a fortune with this. We were thinking to ourselves, we're going to make a fortune with this. And, but it cost $799. So we introduced it on the marketplace, Magnolia Hi-Fi. People lined up to see it. They walk inside, gosh, I have to have this. How much does it cost? $799. Ooh, I'm going to have to go ask my wife. Now you can imagine how that conversation went. And we weren't making a lot of money at $799. It just cost that much. We didn't have the components. But what happened was interesting. Dentists started buying these. We said, what? We started looking at who's buying these. We were sending these things to dental clinics. And we finally decided to go visit some dental clinics, see what they were doing with this. And what they were doing is putting this on their patients. The patients would select a movie they could plug in directly to this, and now they're watching this movie while the dentists are inflicting pain on them. And the dentists were saying, wow, this is great. The patients aren't complaining anymore. I get on with my work and everything, but it is causing another problem. Now I can't get them to leave. See, I can't leave now. This is the good part, But even more remarkable than that is this. This little girl, what is she doing? It was amazing. These kids would go home and ask their parents, when can I go back to the dentist again? So I can, so we said, and the dentist said, they don't seem to be experiencing any pain. So we took this for a while and said, okay, let's investigate it further. So we went on over to the Children's Hospital over here and worked with some doctors who were treating leukemia patients. These are kids that are really sick. And of course, they're administering chemotherapy to these students, to these kids, these patients. And the problem is you have to extract bone marrow to find out the efficacy of the treatment. And these patients are really sick and you can't anesthetize them. So the way you get bone marrow is you stick a needle in the hip and you draw out the bone marrow. And it's so painful, they usually scream. And what we did was give them this setup to put on a headset and the Nintendo controller. And the kid would be bent over playing this game. The physician would put in the needle and the kid would go, and keep going. And the doctors and nurses would look at each other and say, what is going on here, Well, we knew that television numbed the mind. Well, now we know for sure it doesn't. But this started a whole program, and I'll talk about in a few minutes, in pain. But as it turns out, we were way too early with this. Now you can go buy my view for $199, which is my patent. If you want the model, it's probably going to cost a little more, but you can now buy these and variations of this today. And then, of course, that caused a whole bunch of things to happen. The Glasstron, Imagine, Google Glass, all of these things eventually came from that original work. So there are still limitations to these displays. In order to get a wide field of view and a high resolution display, you have to have a lot of resolution and luminance here. And that's difficult to do. Normally in a display, when you have a real object and you're looking at that real object with optics, which is pretty much what we do in all the head-mounted displays today. So you have a lot of pixels here. You may have 1 million pixels that you now collimate, and so they appear, this screen appears at optical infinity, and then that goes into the retina of the eye. I decided, you know, we're never going to get there this way. We're not going to get the field of view, the resolution, things like that we need. What we need to do is actually create 1 pixel and scan it directly on the retina at high speed. So there is no screen anywhere. All there is a beam of light that goes directly to the retina. So this is my patent of the virtual retinal display. It's breakthrough in concept. Not even forming an aerial image, it goes directly to the retina. So it's issued in 1995. Guess what that means? How long do patents last? 20 years. I was too early on this. But nevertheless, we started building these things. Here you see an optical bench with our color display. We had 2 lasers. We had helium neon lasers that provided red light, argon ion that provided a green and blue light. And then we took those light beams and then we modulated them with acousto-optical modulators and then combined them into single fibers, into 1 single fiber. And here you can barely see it. There's a fiber, a single fiber comes up here. And this is a scan head that scans in 2 dimensions into a spherical mirror and a combiner. And then you see this image. You see it, this scanned on your retina, but what you see is an image at optical infinity. It's beautiful. Highly saturated color, very low energy, because you don't want to, of course, you don't want to injure the retina. Very low energy. So here's a little video.
Now, we've all seen pictures and text on computer screens like these, but what if I told you that over in Seattle they're working on a laser system which bypasses the screen altogether and projects a high-resolution colour image straight onto the retina of your eye? It sounds unbelievable, but they've already completed a working prototype. Craig Doyle checks it out.
This is the first full-colour virtual retinal display, or VRD for short. The way it works is, instead of seeing the image on the computer screen, it's painted directly onto my retina by a laser. Now, I know that sounds a little bit dangerous, but the laser is quite low powered, so it won't damage my eye. What I do is, I line up one eye with a little coloured dot I can see. Now, as I move in, the picture gets bigger and bigger and bigger as the dot expands, and now, there, I can see the full picture. Looks like it's hovering in the air about 5 feet in front of me. And it's exceptionally high quality. The flickering is caused by interference with our camera, not the VRD. In fact, the VRD goes 1 step further. Not only can you enter a virtual world, but it lets you overlay those images on the real world.
Now, the incredible thing about VRD is, because the image is put directly onto my eye, there's no need for an intervening screen. So if I lift this up, right, now I can see the picture, and I can see everything else in the room as well. So if I just slide my hand in there, now it looks like the whole picture has been superimposed on my hand.
It's fantastic.
So here you have something that is both AR and VR. If you don't see through, it's VR. If you see through, it's AR. So we went on, continued on with this work. We decided what we had is a scanning aperture. And what we could do is introduce all kinds of things for that scanning aperture. So we built what we call an interactive virtual retinal display. So we were actually tracking eye position at the same time. So you could tell exactly what pixel you're looking at in this VRD. And also we tracked where your head position is using the same technology. And we had funding from several sources on that. Then we realized also, now that you're using coherent light, lasers produce coherent light, what that means is you can shape the light wavefront. What that means is you can shape it so that it appears to be different distances. So that means every pixel can be at a different distance. And that's what happens in the real world. All our displays today put all the pixels at the same distance with collimating lenses. But that's not the way the real world is. And so we have divergence cues that tell us, these are binocular cues, that are giving us cues at different distances, but all of the pixels are still at optical infinity, which is a conflict. That's not what the real world is like. This way, we could actually solve that problem. And we started working on the true 3D display. This technology has been licensed by a company called Magic Leap. Have you guys ever heard of Magic Leap? Okay, they're the ones that they're basically using my original patents for this kind of thing. There's one other thing that was in this patent that was pretty cool. We decided, you know, we don't want to have electromechanical engines that are actually scanning a laser, even though they're really small. We want to do it electronically like we do phased array radars. And if we have microcavity lasers here, and we modulate these cavities, bias them in certain ways, we can control the way the light wavefront goes out. We can even shape that wavefront, and we can scan it as fast as we want to and have unlimited number of picture elements. And so this, what I believe, is the future of basically a phased array scanner is going to take the place of all the other means of doing these things. Now, I didn't get a chance to build this in time, but I think we want to try to do this in the future. Okay, some other things that came out of this, when you're going in a direction, you sort of stumble on things. We decided, well, why can't we just take those fibers that we're laying the image, and we could actually scan them in a raster? And we figured out a way to drive these little fibers. We can even write things with it, and actually turn it into an endoscope. So we built this endoscope that lets us go in the body. We're talking about something that is less than 1 millimeter in diameter, that can image in the body greater than any other endoscope that exists today. It can go into, one of the things we did in the lab is we were imaging inside a rat's bladder. So we were putting this inside the bladder of a rat. Rat wasn't very happy in doing this, but nevertheless, it could be done. And is also in color and 3D. So that's something that was a fallout of what we were doing originally. Okay, now this student shows up, and Linda knows very well, along with me, Mark Billinghurst from New Zealand. And Mark was very interested in what we know today as augmented reality. And the video-based augmented reality, like Pokemon Go and things like that, sort of like that. Anyhow, Mark, along with one of our visiting scholars, Hirokato, got together and started working on this notion of video-based tracking. Using computer vision technology, you can just take a black square, and this is just on an ordinary foam core right here. You can print it on a piece of paper or whatever. Put this black square, and you put a symbol in there, and then you look at it with a set of goggles with a TV camera. TV camera scans this and says, there's a black square, I'm going to start tracking it with 6 degrees of freedom. And oh, by the way, I'm recognizing the symbol that's in there, and it just happens to be a samurai. And so you pull a samurai out of the library and you paste it on that card. So whenever you move that around, it's just like it's there. It's like super glued to this particular thing. So what this meant is it opened up a whole new idea about books. So you know when you're reading books, you're reading a book and you have these images in your mind of what you're reading. And but what if you're reading a book about Cinderella, and you put on your glasses, and what happens? Cinderella's castle pops out of the book. There it is. You can move it around, look in it. You look in the window. Oh, there's some people inside. I want to go. And so you flip a switch, and you go there. Now you're in the book, wandering around in the castle. Now you're switching from outside to in. You wander around the castle, do some things there, decide it's time to leave, you turn the page, and there's another world for you to go into. So this is the magic book technology. And I'll play another little video here.
Welcome back. A new kind of reading material may hit store bookshelves soon.
Q13's Elizabeth Johnson shows us a magic book conjured up at the University of Washington.
This is a story about a Japanese princess, and she's crying here.
It looks like just a regular children's book, but this book can take you on a magic carpet ride of sorts.
When we were children, you know, you'd read books with your parents, and you always want to become part of the story. And so we thought about that, and we thought how we could make that happen.
Mark Billinghurst is on the team of researchers working on the Magic Book Project at the University of Washington's Human Interface Technology Lab.
So when I look at the pages through this headset, I see 3D virtual characters coming out of the pages.
And by simply flipping a switch, you can virtually leap into the scenes.
So here's the samurai, and the samurai is looking a little bit confused because he can't find his horse.
Of course, it's not really magic. The secret is special software written by the researchers and the black squares.
On the pages of the books, we have a picture with a black square around it. And then the way our software works is that the camera recognizes this picture and overlays virtual models on top of this picture.
You need a computer, camera, and virtual reality glasses. Mark says if you already have a PC, the rest should cost about $700. The technology does more than entertain kids.
Let's look behind us. There he is. So that's the evil ninja.
It can be used to show 3D how-to diagrams, to show an ant's eye view of a flower, or to help medical students.
We're working right now with the medical school to build an anatomy textbook so you can see a virtual 3D heart and fly inside the heart.
Elizabeth Johnson, Q13 reports.
The lab is giving away the software for free, and researchers say they've already had interest from a museum and a car company, so you can expect to see the magic book technology in the real world in just a couple years.
Okay, so what happened with this is we formed a company called AR2Works. This is called the AR Toolkit. We had 100,000 downloads of this, open source download. And so we formed this company as the very first AR company. Actually, it's the only AR company that made any money, I think. But we sold it in 2015 to Daiquiri. But it was what got this out to the beginning. Now there are lots of them, and we had natural feature tracking, all this other. We didn't need the cards anymore to do that. But you can see what can happen with augmented reality. We also used it for molecular modeling, how you could have tangible interfaces with various molecules. We also did a project with the Boston Museum of Science, funded by NSF and Lucasfilms, where we actually built Tatooine. And it was an augmented reality. You could actually populate the city of Tatooine in Star Wars to find out what's the optimum placement of the distilleries and things like that. And this toured all over the world, this particular exhibit. Okay, so I'm running out of time, guys. I'm at attempt 3, which is doing some really cool stuff, taking into account what we did before. Let me see if I can buzz through a few of these things quickly for you. You remember the virtual retinal display I showed you before? One day, a guy came into the lab and said that he happened to be on the board of directors of the Washington Technology Center. And he said, I've heard about this virtual retinal display, I want to see it. So we took him down in the lab, we set him in front of an optical bench, had him look into this, and sure enough, you know, you see this amazing picture as you saw in the movie. And he said, well, that's cool, you know, and we said, take your spectacles off. This was one monocular, it was just one eye at the time. So he took his spectacles off. He said, I can still see it as clearly with or without our spectacles. We said, yeah, that's because we're not really using the optical power of the lens of your eye or your spectacles or anything like that. He said, oh, that's interesting. And then on his own, he happened to look with his other eye. And his mouth dropped open. He said, wait a minute, what are you doing? We said, what do you mean? He says, I can see this with my blind eye. We said, what? He says, I'm blind in my left eye, and I can see that image. Oh, yeah? And it turns out he'd been in an automobile accident years before and left scar tissue in his eye. Apparently the retina was still working. There's a lot of scar tissue in there. We were getting through that with the coherent nature of the light we were putting in. And so we went to the medical school, went over to the Department of Ophthalmology, and they started sending patients to us. Sure enough, patients with all kinds of problems were able to see with this, even with age-related macular degeneration. And that started us on a whole different track. And we then got grants from NSF, NIH to work on low vision using the virtual retinal display. By accident. That's what happens with serendipity. It just happened. With this one, I showed you the little kid, right? This now launched a whole new area of research. My colleague Hunter Hoffman, a psychologist, started introducing this to burn clinics. We found it's amazing what happens using VR as a non-pharmaceutical analgesic for pain by controlling the way you think, basically. So here you have a burn pain person who's in the hospital, severely burned, resting in bed, and generally what happens is you can control their pain with morphine. You see here's the amount of pain in terms of different categories, all the way from no pain to excruciating pain. And generally you can keep it down here into this area. But when you go to do any kind of intervention, like wound care, you're going to pull staples out of skin grafts, you're going to put patients in a vat and soak them with water and slough off the dead skin, or you're going to go into physical therapy, the pain shoots through the roof. You can't dose that patient with enough morphine. It shoots right through that. Furthermore, morphine is bad stuff. It's toxic, it's addictive, things like that. Now, if you take those same patients, and here they're playing Nintendo, just looking at a normal screen, or doing wound care, they're in VR. Let's see what happens. Red is just looking at the regular screen. Blue is VR. Worst pain, this is a scale. This is the pain level here, up to 10. The worst pain you experience, the unpleasantness of a pain, the time spent thinking about pain, anxiety, and your feeling of presence in the space. We thought, wow, well, that probably will only work one time, right? Because of the novelty of VR. Just the opposite. It gets better the more they're exposed to this. So this started our whole division of the lab working on this. Here is the fiber optics. There's you have a patient inside a water vat where you're sloughing off the dead skin. Fiber optics relay the image because you have any electricity there on your head. You're doing this. Then we decided, well, what's really going on in the brain? So down in the medical center, we put these, mainly grad students. We can inflict pain on graduate students more than usual. We have great ways of torturing. We studied this. The best way of inflicting pain is with a shock to the tooth pulp. You run a current through the tooth, you know. Shh, you can really, and so there are other techniques like putting your hand in ice water. We have an ice scale that goes up in pain. But in this case, we're actually heating up the bottom of their feet. And so we inflict pain and find out what happens to the brain when pain is going on. And this is with an fMRI system in the coil with fiber optics come in, again, because you can't put anything metal in there. And so this is what we find out. You know, this is the pain centers being lit up here without any VR. But look what happens with VR. Metabolic activity and the pain center goes away, and look what lights up here in the frontal lobe. It really works because it distracts you. Turns out, in order to experience pain, you have to be conscious of it. So this is a tool that's now being used all over the place for not only pain, but for PTSD, for phobia treatment, of which we've done a lot as well. I'm out of time. I have lots of other stuff to talk about, but let me show you just one little thing here, I guess. What is this? I think if we're looking for a killer application in VR, it's really education and training. In the long term, that's what it's going to be. So how do we awaken and enlighten and engage students? You know, this kid can't wait to get home to play Grand Theft Auto or Fortnite or whatever it is, right? So we began probing this whole area as early as '91 with the Pacific Science Center, where we had kids build their own virtual worlds and go into them. These were 9 to 14-year-olds who had no experience with VR. In 4 days built a world, and they each had a polygon allowance. They can only spend so many polygons on their part of the world because we couldn't render it that fast. Yeah. So these are some of the worlds that they built. Then Garfield High School, we did a project with Garfield High School in the chemistry department. And we wanted to find out, does it really work in the classroom? And what we did was we had the kids use the traditional methods with a blackboard. We had a treatment that was a computer tutorial system, looking at a monitor, and then we had a virtual world where you'd go inside this virtual world, be shrink to the size of an atom, and then you would build an atom, atomic structure. Protons, neutrons, you put them together, reach out of the bins, put them together. Mind you, this may not be how it really works, but you put them together, and then you pick an electron out of the bin, you give it an energy level and a spin, you put it in an orbit, and then you start building greater atomic numbers that way. So what we want to do is find out, just because the chemistry teacher said they really aren't getting this. They aren't getting these electron orbitals. So after this module, we tested all the students. The kids who were making A's didn't make any difference which treatment they had, the VR or the lecture. But the kids that were making C's and D's and failing, that did the VR one, caught up with the smart kids. And when we tested them a year later, they were better. Now what this told us, and there's nothing wrong with those kids to begin with, they just learn a different way. And that the pedagogy is wrong, expecting everybody to learn the same. Give them a chance to get involved, use their hands, eye coordination, let them do that. So this led to many, many more studies. Over many years, we even went out to, with the US West Foundation, we took it out to 8,000 kids in Washington State and the state of Nebraska with our VRRV. And this, they didn't go into the van. This equipment was held in the van. Then we took it out and set it up. But and 350 of those kids built virtual worlds. And then we had this project we just in the process of doing. We finished the first year of it in June, last June. And let me show you just a little video of that experience.
Today is start going over just some of the basics, how to add objects, how to manipulate them.
What was that like?
Oh, it's so real. Like, yeah. Whoa. Oh my gosh. That was so cool.
the hang gliding, when you hit something, it was so realistic. I like fell over, like almost fell over twice.
Brian, what do you think? So you want to build some worlds?
Yes.
All right.
Precious donut. It'll be worth a lot. It's a price gem of Donutlandia. We made Donutlandia. Donutlandia.
You can build things, and you can practice your creativity levels. Like if you want to be an engineer, you can practice doing that.
Teeny sunglasses. I would almost not even go with like sunglasses. I would even say it'd almost be like contacts or something.
Yeah.
That are like just
like little tiny contact lenses that you can just pop into your eyes.
Okay, these were sixth graders, 11 and 12 years old. They had to learn Unity, and in order to do this, and they were divided into 4 groups, and they needed to build content that taught gravity, scale, light, and momentum to other sixth graders. And so we had about 20 of them. You notice there's some older kids there. Those are my students from here. We had about 12, 15 UW engineering students that were actually being mentors of those kids. And of course, they were role models. They sort of fell in love with each other. The old kids to the young kids and the young kids to the old kids. Now we're actually, this was an after-school program last year. This year we're in the classroom. We're actually, students every day are doing VR in the classroom at the Robert Eagle Staff Middle School here in North Seattle. So I'm going to stop there, and I have another whole lecture, by the way, era of you that I'm cutting out here, but I thought it'd be good to have some time for questions. Thank you.
So, question I had was, you showed so many different applications of VR, and if any one of us went on Amazon, we'd see, like, say, the HTC Vive. It's $500 or something. The newest, most future, greatest VR in the future is probably going to cost even more money. And right now, the cheapest is $200. You could buy a Windows mixed reality headset from several different companies. What I want to know is, do you expect it to be part of everyday life? Because a lot of the things you showed was specialized application. You aren't going to have a house on fire and a firefighter using it every single day. You don't go to the dentist every day. Like, even now, I've gone through so much. I got into the CSE program and all that, and I have access to the VR lab. Not very many people do. Right now, it still feels very specialized. Like, I guess what I really want to ask, do you ever expect it to reach a point where it's become part of everyday life?
Did everybody hear the question? Great question. I believe that, I agree with you. I mean, it's cheap compared to what it used to cost us to do this. But It's really to the point now where it's getting interesting because the price tag is going down. As you know, with some of the new gear, I mean with the Oculus Go, and now with the Oculus Quest and with the Vive Focus and all these kind of things, I think the manufacturers are realizing, that they're shooting themselves in the foot if they think people are going to spend, $1,500 for this, especially consumers. So what I think is going to kick in for a while, we talked about this before, about enterprise. I think we're going to see a growth now of enterprise applications. They're sort of going to carry the ball and help us develop the technologies where the price point goes down even further. There's no reason why we can't mint these things. There's nothing really there that ultimately has to cost a lot of money. If there's just a bag of parts, the cost to build is really more expensive than the parts. So I think we will have the capability to have these systems that are like cell phones. And I mean, think about what happened here. Not many people used to be able to afford these things. Now the price came way down. Now they're going back up again, of course. But it's amazing what's happening, and all that's packed in that cell phone. And not only the, your ability to communicate, but the camera and all the other stuff that's built in there, the gyros, the accelerometers, GPS. It's really amazing. It's there. And now with 5G coming along, 6G, with streaming, that means that you can reduce the amount of computational power you have to have in the device itself, ultimately. So it's sort of like going to be interactive radio television. It's going to be broadcast, and you can have that. So I think the price will come way down. It's still going to take a few years to get to a point where, you're going to be willing to spend a couple $100, and you're going to get a full VR kit. But I do think it's important to have the high end too, because if you probably have played with the Vive Pro and the wireless systems and all this other stuff, it's pretty good. Those are pretty good. We have new Pimax coming. I haven't gotten it yet, but it's even wider field of view, and so yeah.
Would you expect this kind of situation where you're married to someone, you're heading out to go to work, you ask your wife, it's like, do you think it's going to rain? She'll put on a VR headset, and so it's like, yeah, it's going to rain. And I guess I'll take my umbrella. Do you think that kind of thing's going to happen?
You all can do that. You just sort of ask Siri or Alexa, what to...
An everyday use of it,
Yeah. Well, it's going to be like everybody will use it every day, just like you use television, like you use cell phones. It's going to be a new medium that that is going to be universal. We'll use it in our lives for whatever it's good for. Now, it's not going to solve all problems, but it will be, it's going to add that. And by the way, what VR does do is it awakens our spatial memory. When we go into VR puts a place inside of us. And that awakens our spatial memory to the extent that we never forget it. We never forget a place. That's why it worked with those chemistry students, and why it works with pretty much every one of you who've been in a virtual world, had a good experience in a virtual world, you'll always remember it.
So if someone needs to go, it's okay. You can just leave quietly, and the rest you can keep doing questions if you want.
So what are it seems like the technical part of making VR where people don't get sick, we're kind of there, mostly. So in some of these applications, you're starting to do research in particular applications. Like, what are the real gaps that we need to do research in to make a lot of these applications work?
Okay, very good question. There are some things that I'm greatly concerned about. We are deeply coupling our visual system, human visual system, to these devices. And we don't still understand completely how that works. And one of the areas, of course, is this conflict between the vergence cues and the accommodative cues. And we need to get to the bottom of that and solve that. The second is the longitudinal effects of that. Longitudinal effects of wearing VR every day when you have those differences than what you'd have in the real world. We've got to do the research, and that probably ought to be sponsored by NSF and people like that, the NIH, to work out those things. Also, we don't understand what's happening with the peripheral retina. This is one of the things. I just have an NSF grant to work on that. Out here, we've done studies that take us out to 180 degrees. And we know that even at 180 degrees, we are getting stuff in. But the retina takes us all out to 210 degrees. We were doing a study down at the lab in Benjamin Hall earlier this week. That was yesterday. And last week, where we were showing symbols to subjects that there were different symbols, 5 different symbols, back here at 230 degrees, and they were getting them. But they said, I didn't see them. I can't see back there. I didn't see them, but they came up with the right answer. Wow, that's interesting. Because that means that what's happening is out here, we're processing that in subconscious, subliminally. There's a lot going on there that we don't know. So that's another whole area that we need to solve. So there's some of these fundamental things that we want to do no harm. Now with the the march of technology, with the computational capacity we have and the way we allocate it, 5G networks and beyond, it isn't going to be an issue of getting the pixels. It's how you now, pixels to the device, that's how you get the pixels from the device into your eyes. It becomes important. And how big a field of view do you need? I mean, right now we're running about 100 to 110 degrees in these devices, when in fact we're seeing stuff out here way beyond. Simulator sickness, that's a big deal. And we know how to manage it, but we have a bunch of cowboys out there making software, making games and things like that, and making people sick. We know why they're getting sick. But how do we get to the standards that keep people from introducing that in the marketplace? Because you don't want people to get sick in VR. Other question, yes?
Can you briefly talk about its applications in dementia care?
Yes. Dementia is another one of those situations where, with mild cognitive impairment and things like that, you want to keep a person active. A lot of the times, most of my understanding, again, is a lot of dementia comes from basically you not having enough stimulation in many cases. You look at the patients who have these, and they're usually in places where they don't have a lot of interactivity. They're not being stimulated, things like that. What this can do is, what VR can do is put them in places where they have to do things. And oh, by the way, we can also assess objectively the status they have. Right now it's so subjective, where a physician evaluates just how bad off a person is. But if we look at the signals we get from eye movement, head movement, speech, movement of the hands and arms, and interacting with that world, we know a lot of what's going on. And then we can test them and how they're remembering, and then we can run them up a slope with adaptive. We watch what they're doing and we adapt on the fly to take them up a slope to improve their cognitive abilities. Now, if we're talking about Alzheimer's, where you have plaque filling up your white matter and things like that, all bets may be off there, and because that's a chemical thing you're going to have to solve. But the onset of dementia can be ameliorated by people being active cognitively. It says if you don't use it, you lose it. And we have a bunch of dementia projects underway, by the way, right now. Other questions? Yes?
It sounds like you were fortunate to be in military research from early on. I'm kind of curious what you can talk about, what do you think hasn't made it out yet that might change the next 10, 20 years?
Well, the military's 20, 30 years ahead of us out here. And the reason is you have these amazing budgets. When I first arrived at UW, the first day here on campus, the dean invited me into his office. And he said, okay, Tom, now that you're here, I have to give you begging lessons. I said, what? He said, you've been working for the DOD. Now you're an academic. You have to learn to beg. And I thought he was kidding. You have to shake hands like this, And but at the same time, what the military doesn't have are these guys. And this is what's magic. This is the magic dust, students. And students who are, you know, are bright and who have great ideas, and we take risks. We can take some risks. When you have in the job I was in, you had to get it right, you know, and you were trying to counter some real threats. And so it's serious business. Here we can take some chances and do some things that, and by the way, if we're not failing, we aren't trying hard enough, because we should be pushing that boundary way out there. I don't know if that answered your question, but okay. Other questions?
Thank you so much.
Thanks, guys. Okay.